On this episode, can something as simple and low-tech as ball bearings protect a house from a devastating earthquake? Welcome to Smash Lab, where 4 maverick inventors engineer outrageous new ways to make the world better. The team is Kevin Cook, ideas guy.
What we gotta do is we gotta make it huge.
Chuck Messer, engineer.
I think the car's gonna smash through, it's gonna blow up, hit the barrier.
Deanne Bell, scientist.
So the car hit it, that energy transferred here, and then it hit the other one.
And Nick Blair, designer.
If it goes wrong, it could go horribly wrong, really.
Smash Lab. At an airport warehouse, Chuck and Kevin check out an ingenious way to handle big loads. Dotting a floor with ball bearings gets rid of nearly all friction. Even the heaviest cargoes glide effortlessly.
Floors covered with these captive ball bearings, just like in the holds of some aircraft. Lets you move huge containers around with ease.
How much do you think this guy weighs?
This weighs 2,300 pounds, as much as a small car.
It's kind of like just pushing something around on a blanket of air.
The team hopes to use this method in a surprising way to protect a house in an earthquake. At Smash Lab, Chuck and Kevin show Nick and Deanne their outrageous idea.
Nice! Wow, Kev.
What is that thing?
Captive ball bearings.
Thinking we're going to use this to make a house earthquake-proof.
It sounds like a feasible idea, yeah.
Here's the idea. Earth. And this is the house. Earth moves underneath. The house freely slides on top.
So you're trying to use these ball bearings to create kind of a frictionless surface, right?
Earthquakes shake the ground violently. The team wants to isolate a house from ground movement by putting ball bearings between the foundation and the building. Riding on a layer of bearings, the house should stay steady, even though the ground below is shaking. We rate earthquakes on the Richter scale. It's hard to even feel a quake of less than 2.0, but anything above 4.0 can shake buildings and cause serious damage. And the higher the Richter number, the worse it gets. To show his accomplices what they're up against, Kevin's set up a demo.
Earthquake on wheels.
Well, that's pretty cool.
Big hydraulic
Hi, Dean.
trailer, huh?
Welcome to the Big Shaker.
The earthquake simulator is outfitted like a home to show what happens in a quake.
Tapping the mainframe here.
This is the first sofa I've ever seen with seatbelts.
With that bookcase in striking distance, Deanne plays it safe.
All right, Dean, give us a small earthquake.
All right, here we go.
This gentle tremor simulates a 4.0 on the Richter scale. The structure holds, but not the contents. And that's no joke. In real quakes, falling furniture causes more than 50% of injuries. To prevent this, the team needs to create a ball bearing system that keeps their test house almost still during a quake.
That's a small earthquake, huh?
Yikes.
Dean, give us an extreme earthquake, please.
Clear.
The next shake simulates an 8.0 on the Richter scale. Much, much more powerful. Throughout, Deanne hardly stirs. The roller chair is doing for her what the team hopes their system will do for a house, isolated from movement below.
That's serious,
It's because I'm on rollers. That's why I'm not feeling it.
You know, it looked like it was working pretty well, too. It was sliding back and forth, and we were going the other way, and you were staying pretty still.
Even though that's a simplified version of an earthquake, there's still a lot going on.
Yeah, I noticed 2 types of movement. There's definitely an up and down
Right.
and a back and forth movement.
Deanne knows the real danger in a quake is the Earth's sideways action.
What we're really concerned with is that side-to-side movement, or lateral movement. And it's how much it moves and how fast it moves.
So if you think about it, it's like the Earth's foundation underneath you. If it moves really slowly, you're just going to kind of move with it, right? But if it moves really fast and really quick, you're going to kind of buckle, just like a house, and fall to the ground.
That's easy to illustrate.
Okay, so you guys are in a good position to be the earthquake.
All right.
Kev, you want to be the house?
I'm gonna be the house.
You're going to be the house. So we're going to pull slowly towards Nick. Ready? Kev, do your best to stand up.
No problem.
Nice.
Not so bad, yeah?
Yeah. The Red Surfer.
Okay, now we're going to go slowly towards Chuck, and then really quickly now.
Oh!
Oh, man, you all right?
Yeah, I'm good. I'm good.
Okay, really?
I'm good. That was beautiful.
Good job, Kev.
Yeah. Well, Kevin fell relatively easy.
I didn't go down that easy.
Yeah, easy.
I mean, this is fun and all, but we need to mock up some kind of experiment to simulate that with a house. We're just looking for like a slow motion in one direction and a nice big jerk in the other.
Right. So something powered by a truck or something like that.
Preferably with a house on it or a building of some sort.
That we can topple, right?
Yeah.
Let's mock it up.
Why don't we draw this out?
The guys want to see how rapid sideways movement wrecks buildings. They're going to set a brick building on wheels and slam it into a concrete barrier. At impact, the structure should behave as it would in a quake, with violent horizontal force ripping it off its base. Nick and Chuck rig pulleys for the test. While outside, Kevin goes cubist.
We're gonna have an unveiling.
It's little. Check it out. Gotta see what it is.
It's a house.
Wait a minute.
Well,
nice.
kind of.
It appears to be a box.
Solid walls make the box a lot sturdier.
Actually, it's pretty well set
I'll
up.
find the door. Hold on. There is no door.
Or any windows.
Or any features whatsoever.
Resembling a house.
If you guys really want a house, I can set you up.
How
Wow.
about a flower box?
There's your house.
For the test, a truck will be attached to the house by a steel cable and will then pull it at speed.
We ready?
Ready.
All right.
Let's get in.
A final check, then it's ready, steady, go. The house is a mess, but that's a good thing. The damage shows how a quake's lateral motion can wrench a building off its foundation.
It was a sudden deceleration, which is much like what you have in an earthquake when it stops going one way and starts going the other way.
All we wanted to accomplish is see if we could pull it down with lateral movement, and that's exactly what we did.
Yeah.
But what we saw here with the shearing here at the mortar, I think is very representative of what we're going to see in an earthquake. You know, if you have a brick building, all those bricks are going to want to kind of separate apart right here at their connection point.
The test has been a success, showing how a quake's lateral movement destroys a house. Coming up, the team is now ready to start building systems they hope will defeat those forces. To do that, they have to create an earthquake of their own. And that will be no easy job. The Smash Lab team plans to earthquake-proof a house with ball bearings. This could be a low-tech, low-cost solution to a huge problem, if they can simulate a quake's speed and power.
That we can topple, right?
Yeah. We need an earthquake, and we can't really wait around for one to happen, and we can't just order one up. So we're gonna have to figure out a way to create our own. Well, we need to build ourselves a shake table.
Yes, we do.
Something medium scale that we can try out all kinds of concepts. Reasonably powerful too. Let's see if we can mock it up some way and play around with it.
We need to play around and make sure our idea works.
The guy's plan is to use air pistons to mimic a quake's sudden jolts. To check the idea out, they experiment with bike pumps, running air backwards through them to create jerky movement.
Oh, that's great. I think you're onto something.
Strong enough. Ready for a test?
No.
All right. This actually works.
Score 1 for the pumps. Next, build an air-powered shake table. Meanwhile, Nick and Deanne are designing a model house in the style most at risk in a quake.
A typical American single-story home actually does fairly well in earthquakes. It's when you get multiple stories and you have like a carport or you're missing a wall. Those situations are when homes get structurally compromised and you're a little bit more at risk with an earthquake.
Okay, well, I think we should design in both of those vulnerable points into the scale model.
Including a carport means the first floor will be short one wall and much less solid. A second story raises the center of gravity. Extra height further reduces stability.
Okay, let's build it.
On the far side of the lab, Chuck and Kevin finish the shake table. If it works, they're ready to test.
Well, let's crank it up.
Their gizmo delivers sudden, unpredictable movements, similar to what happens in a quake. The shake table is ready. To survive, the test house needs protection. The team plans to use base isolation systems that put a layer of bearings between house and foundation. To test the concept, the guys rig up a crude arrangement.
This is a good start. The first step on our way to the final base isolation system.
With everything ready, it's time to test.
We have a shake table.
It's cool, huh?
It's violent.
It's a little brutal.
Yeah, I'm a little reluctant to put our little rickety house
Put it
down.
on there.
All right.
So the general idea here is we're thinking of isolation systems, right? We want the ground to shake violently back and forth, and we want that house to be standing there unaffected.
And what we got here is the most basic version of an isolation system. It's just ball bearings on a board.
Okay, watch your fingers. Let's test it.
Yeah, that's pretty cool.
Kind of works.
Yeah,
The ball bearings are making the house just roll around a little bit.
Yeah, we definitely have some drifting going on, so that's something we'll need to address. But it looks good.
The bearings do isolate the test house from the worst shakes, but the house is drifting. They need to hold it in place. It's hard to restrain a full-size house that's riding on bearings. The structure needs to stay still, but also needs flexibility. A tether that is too weak will snap, and the house will pull free. But if it's too strong, it won't allow enough movement, and the house will shake, maybe to the ground. Chuck has an idea.
I'm thinking either springs, bungees, maybe you mount them here and here, just to return it back to position. Could be blocks of rubber, anything like that.
But Deanne has a completely different suggestion.
Right, well, we're just looking to restrain it. We can do that with springs, or I think we might be able to do it with gravity. As this ball moves in this dish, obviously gravity is constantly wanting to bring it back to center. Now, there's a system in place under skyscrapers already where they put the entire skyscraper on a bunch of little dishes just like this. And as the earthquake comes, it shakes, but it always comes back to center. Now, granted, a skyscraper is huge, there's a lot of friction, and it's pretty expensive. But I think that we might be able to scale this down to a house.
They decide to develop both systems. A contest then, with victory going to the idea that works best. Coming up, Nick and Deanne try to get gravity to work for them, while Kevin and Chuck build a restraining system with springs. Either way, the stakes are high. If their houses collapse, so do their hopes for a quake-proof system.
What did you do?
The Smash Lab team has a daring idea. Use bearings to keep earthquakes from wrecking houses. The first try worked, sort of.
That's pretty cool.
But the house drifted. They have to find a way to hold it still. To do that, the team split up. Each crew is trying to find a different approach. Nick and Deanne want to restrain a house using bowls and gravity. Chuck and Kevin are trying springs, and already Chuck spots trouble.
With the springs, I expect it to return to its position, but probably bounce back and forth some. In an earthquake where you have a repetitive motion, they could potentially amplify that motion. Yeah, you see that jiggle back and forth? That's bad.
That's why we can't just use springs by themselves.
Right.
Their system needs more.
So I think we should look at dampers.
Like truck shocks.
Yeah, I mean, that's what they're designed to do. They absorb energy and they prevent it from the springs from bouncing back and forth.
Most shock absorbers on trucks have two main parts: a spring that flexes, absorbing bumps in the road, and a damper that keeps the spring from moving too much. The damper's piston compresses only slightly as the vehicle's motion forces oil through tiny holes. The oil's resistance keeps the spring from bouncing too much. A system like this could calm Chuck and Kevin's springs.
We should try making our own dampener here, some sort of liquid hydraulics, but in a much smaller scale than what everybody's used to, just for use on our mini quake table.
Yeah.
Check it out.
Nick and Deanne are trying another approach, putting the bearings in bowl-shaped dishes. It's similar to a system used in large buildings, but never before tried on American houses.
So the general idea here is as we have one big shift, it kind of goes uphill a little bit.
Yep, like this.
But because of the nature of the dish, it's going to kind of rock back downhill.
Exactly.
So it's kind of natural equilibrium.
Exactly, yeah. And we'll have 4 points of contact
Great.
around this thing, so.
Their system uses gravity. The house rides on bearings laid in bowls. A quake will send the house up the side of the bowl, but not too much. Gravity should fight this and keep the house on center. Time to go down to Shaky Town. Well, Shaky Table anyway.
All right.
Should we give it a go?
Yeah, give it a go, just by itself.
Jumping. If we add more weight, we're going to get a little more friction in there.
Okay, so it came off the platform, but this is clearly too light.
Yeah, I mean, the thing with a friction pendulum design is they're typically used on skyscrapers. That's why they work so well, is there's so much weight from that skyscraper pushing down, creating that friction that's necessary to kind of keep this in place.
Right. And actually, this model at scale is a lot lighter than an actual house would be. So I think it would be fair for us to add maybe a few weights, like sandbags or something like that, to weight it down and get a little closer to reality.
The increase in weight keeps the bearings in the bowls, but the house still moves too much. Deanne thinks the bowl's shape may be to blame.
It's definitely better. It's kind of going uphill a little bit and coming back down, but if that was a lot more concave, there'd be a lot more gravity to fight. Like in this case, it's fairly shallow, so you're not fighting all that much gravity. And let me just geek out for 1 second, okay? So...
Calculating curves is a math problem right up Deanne's alley. Meanwhile, Chuck and Kevin nearly have the shock absorbers ready.
This is too loose, and it's just letting the air escape right past it. Teflon tape. It's very thin, and it slides easily. Oh yeah, that's great.
You can tell it makes a difference? I'm sure.
Yeah, you can. There's 5 holes, so we can cover up any number of the holes and get different amounts of damping. Okay, works pretty well. Looks like we fashioned ourselves a pretty decent damper.
Let's take it to the shake table.
They muscle the shocks into place.
Attracted?
Let's see if it works.
You sure?
Yes.
Definitely dampers make this whole system work.
Yeah, it quiets the resonance, so it doesn't just sit there and spring back and forth all day.
One boop, another, right back to its original position. Springs and dampers.
They think a spring and damper system will work on a larger scale, too. Deanne solves the bowl equation. Now she knows just the curve for the bowls that hold the bearings.
So this is it, 88 inches.
So we need an 88-inch arc on a ramp, basically like a half pipe.
The perfect arc. A precise slope that keeps the bearings from moving too much.
Let's build it.
The shake table will only move in one direction. So for their test, They don't need an entire bowl. A cross-section will do.
There you go. All right.
5.
Oh, you're timing it?
I went 1, 2,
okay.
3, 4, 5.
Gravity does stop the movement, but not quickly enough.
Let's see if my weight makes any difference. 2, 3, 4.
They're gonna need more than weight to stop the movement.
We want to actually dampen the response, then we do need to introduce friction.
Well, why don't we actually add something to this substrate like rubber?
Yeah, let's give it a go.
Just lay 'em.
A rubber layer might add friction, reducing movement.
Wow. Success!
I love it. I think we should do one last thing. I think we should actually move the ground as opposed to moving the platform.
This test pits their system against real motion. The pole won't move a bit, but Deanne is floating free. If the system isolates her from the movement below, her head will stay near the pole, proving that the system works.
I don't think I'm moving! You are the best earthquake ever.
Thank you.
I was staying right here. I was completely isolated.
Perfect. Well, this is basically a smaller representation of what we'll do on a large scale then.
Scale it up, 2-story home.
Yep.
Bring on the earthquake.
The two rival systems seem to work, in miniature that is, so the teams decide to take both to full scale. Coming up, their quake-proofing systems ride the monster of Shakedown Street. The Smash Lab team has devised 2 ways to quake-proof a house. Now they're ready for full-scale tests on a gigantic shake table.
Success!
I love it.
All right, hey, we're good to go.
Little more, Gadget. Bring it. Hold that.
We need more over here. We need more over
It takes a small army to pull off the construction.
We'll just tack one end and then get the other one on.
Every time you fix your end, my end goes wrong.
Well, we'll just
Every
tack.
time I fix my end.
And to go with the giant shake table, construction begins on full-size houses. They deliberately ignore building code. They want their houses to have structural flaws. Each ground floor is missing a wall, the way a house with a carport would. A second story adds height, raising the center of gravity and reducing stability.
So the structural integrity of this house really lies in the strength in numbers type of thing. So all the individual fasteners on the clapboard, the drywall are really what's keeping it together. So when the structure becomes fatigued, it's really going to start to fail here. And once that happens, the thing is just going to catastrophically fall apart. And hopefully our base isolation system is going to prevent that from happening.
These houses will endure roughly the same ground movement that was caused when a bad quake rocked Northridge, California in 1994. At 6.7 on the Richter scale, Northridge wasn't one of America's biggest earthquakes, but the ground movement set a speed record, making Northridge one of the most destructive U.S. quakes ever. The test tremors will come courtesy of an 18-foot square shake table that the team custom built. A 100-horsepower motor will create the quake.
Can we turn that on and see how it's running?
I'll kill the power.
The table only moves sideways, not up and down, but its movement simulates the destructive lateral forces of a quake.
It goes back and forth as far as we want it or as little as we want it, and we can shake it as fast or as slow as we want it. It's pretty cool.
This is really something to behold.
Gearing, cramping arms.
Yeah, it's beautiful.
I think we should try to maybe scale up small, medium, large on the earthquake size,
Right.
and then also trying to kick a big peak ground acceleration to try to rip the house off its foundation.
Deanne calculates the speeds needed to simulate the Northridge quake's lateral ground movement.
We're going big time.
She'll run the table for just 15 seconds, exactly how long tremors took to damage 25,000 homes. The first test will reproduce the force hitting a house 40 miles from Northridge. The second will show what happened to homes close to the quake's epicenter. If the houses survive, they get subjected to a third set of tremors, worse than anything ever recorded. It's time for the teams to get their ball bearing systems ready for the test.
All right, so we have to make 4 roller plates to go in each corner of the table.
Yeah, and the house is pretty big. We've got each of these plates cut, and if we just mount these plates on the underside of the house and then have a surface for it to roll on, it should work.
At each corner of the house, they'll weld plates that hold bearings. Those frictionless surfaces should isolate the house from any ground movement. Shock absorbers will keep the house on the table and dampen movement. But every bearing has to touch the base or the system could fail.
The problem is we've got these 700-pound capacity roller bearings.
Yeah.
And which means we're going to have to use
a lot of them
per corner.
Right.
And the problem with that is it's possible to warp the steel a little bit and have maybe only 1 or 2 contacting. And if that's the case, they'll fail because they can't possibly handle that load.
But Chuck has a simple solution.
What we have is a rubber sheet. It's just some polyurethane rubber put on there, and then we bolt all these to the plate. The rubber should give us a little bit of give, so the one that's sticking a little too far out gets compressed, and they all equalize in force.
Yeah, when the weight's coming down on one of these ball bearings, the rubber's just going to squeeze, so they're all even instead of just 1 or 2 touching. Yeah. They're all going to touch now the rubber's underneath.
I think it's a decent workaround.
Nick and Deanne also have their isolation system about ready.
So we adhered. I can already feel the dampening happening. It's beautiful. So we just need these mounted to the undercarriage of the house.
Their system also mounts ball bearings at the corners. Concave runners hold the bearings in place. When the shaking starts, the house should ride above it unaffected. If the motion does get through, the gentle rise and fall of the house on the runners should cancel it out. Rubber on the runners adds friction, further reducing movement.
So this is it, huh?
All right.
Simple, but beautiful, and it's gonna work like a charm.
I can't wait to see it work.
Sounds like your house shaking back and forth is going to look a little different from our house shaking back and
It's
forth.
gonna go up and down, too.
Yeah.
If this rubber works like we want it to, it's actually going to isolate it, and hopefully it'll stay a lot more still than we saw with you guys.
It'll hopefully just do this. Just a little bit.
Coming up, quake-proof designs get the ultimate test. The equivalent of one of the biggest earthquake ground movements ever recorded. Can they possibly survive this? The Smash Lab team finally has 2 full-size houses and a machine powerful enough to shake them to pieces. This test of engineering skills will be seismic. First up, Kevin and Chuck's system.
All right, we have our crane ready to put our house on the shake table and see what happens, and I'm pumped about it. I can't wait.
You want to push your corner? We gotta rotate this, yeah?
Now both teams' ideas have to face reality, and all those bearings have to touch the table or their system won't work.
Hey, Kevin, check those balls over there. Are they all touching?
Oh, yeah.
That's cool, huh, Kevin?
Yeah, it works.
Okay, so we just need to get this thing welded and get the shocks on. We're good to go.
Excellent.
Then we can start shaking.
The truck shocks go on.
All right, it's not very far. It's only 1.5 inches.
Chuck and Kevin are hoping they'll stifle movement and keep the house from sliding.
Almost. There it is.
Well,
I think this is it.
I'll say we try it.
One last job, interior design. To succeed, each house has to stay intact and keep its contents upright.
It feels comfortable in here now.
I like that.
Yeah, I like that feeling once you first get moved in, you know? You get the boxes unpacked.
All right, guys, no forcing around. Let's shake this bad boy down.
Got it. All right.
First time around, the house will shake back and forth 1 inch for 15 seconds. That's what happened in neighborhoods 40 miles from the heart of the Northridge quake, the last big one to hit California. Time for final checks.
so we've got everything set up. You guys ready?
Oh, yeah.
Can't wait.
Okay. So the first test.
Wussy earthquake is what I say.
Passing car.
You gotta start small.
I know, you're right. You're absolutely right. And this is the shakedown test for the shake system, too. So we don't want to overdo it, the first one. All right, let's get it rolling. All right, power on. You can see the base isolation system working.
Yeah, it's working. The house is still definitely moving, though. You see that?
Oh, it's moving. I expect it to be moving.
See it actually flopping a little bit?
Question is it moving more gently than the house? Okay.
That was nothing.
Success. Maybe. The house survived, but what about the decor?
Whoa! You guys should see it up here. Nothing happened. Really? Nothing.
Chuck and Kevin's system passes with flying colors.
Okay, so that was pretty light earthquake, just like we expected.
No sweat, man.
Easy.
The isolation system was working. You could see those springs compressing and letting go.
Totally. Even that long, thin flower pot was still standing up straight.
Oh, was it?
Yeah, nothing moved.
If that isolation system wasn't there, it would have done a lot more damage upstairs.
Oh, for sure.
You saw the whole house going back and forth and responded. Like, you can't underestimate the power of what we've done.
Now Nick and Deanne submit their house for a moderate shaking.
Don't want to be on the rivet.
I'm inside. I'm on the inside rivet line.
Okay.
When the steel hits rubber, there's big trouble.
So this is a bit alarming. We got a little more slop in that rubber than we wanted.
It's the ripple effect. And it could end catastrophically with a tear.
We're going to see it.
Yep.
And if there's a problem, we'll cross that bridge when we come to it.
It's too late. There's no going back. Furnishings in place. The house awaits the shake. All eyes are on those mounts.
All right, power on.
And speed.
As they feared, the bearings are ripping the rubber.
So you can see the rubber tearing up on the other side there. See it?
The house survives, but the system is damaged.
How's it look over there?
That's bad news, huh?
Yeah, we put a hole directly through.
Next, a major quake is still to come, and it's looking bad
That's
for
not
Nick
cool.
and Deanne.
That's not cool at all.
The Smash Lab team is testing two very different quake-proofing systems. One uses gravity, the other uses truck shocks. Both are trying to keep the test houses from moving too much. Each house survived a minor quake, but not without problems. Nick and Deanne's system relies on a rubber liner, which the house's weight and movement tore up.
How's it look over there?
That's bad news, huh?
Yeah, we put a hole directly through. Not the most desirable response.
Yikes.
That's too bad.
I say we slice it off entirely, just pull it out.
But you lose your damping system.
I think we can still get there with just the pendulum itself.
But all is not lost.
Plants up, the lance up, even the bowls are still on the shelf.
No damage to house or contents, entitling them to even more abuse. The second test will simulate what happened close to the epicenter of the 1994 quake that hit Northridge, California. It had one of the most powerful ground movements ever recorded. To simulate the effect, the team sets the shake table to shimmy for 4 inches for 15 seconds.
This time we're going to crank up the amplitude to 4 inches. Did you guys set that, dial it in already?
4 inches set.
Lined up.
All right.
What do you think, guys? Staying up or coming down?
Staying up.
Absolutely staying up, man. Everything was standing up upstairs. I mean, if anything fell, I might have some doubts, but everything was upright.
It's staying up.
This is the closest thing we have to an accurate earthquake.
Chuck and Kevin's system is first in line for the Northridge epicenter treatment.
This is the one we need to succeed at. This is the one that you see on TV and all the houses are down, a lot of damage. This is the one everybody worries about. If we can succeed here, and we have great base isolation systems.
They may feel confident, but in 1994, the real thing damaged 25,000 California homes. To succeed, the house has to survive an equally brutal shakedown.
Okay, you guys all set?
Go ahead, Kevin.
Powering on. Whoa.
Yeah, look at that. That's cool.
I thought I was doing this a little bit, but it's doing that.
Flex now, you see that?
Oh, yeah, look at that whole wall's bowing.
Oh, yeah.
And 3, 2, 1, end time.
But it's up.
That system is so freaking impressive.
It is awesome. It is totally cool.
Walls and windows moved, but the house stayed intact. Inside, the news is not as good.
Oh, not quite the same story.
All right. We have some fallen bookshelves up here.
The vase is down. The bookshelf is down.
Oh, yeah, but if you were sitting there, that wouldn't have been so fun.
Yeah, that'd have been kind of chaotic, you know, watching your favorite movie or something like that. Just what
The
the thing kinda just came
largest
down. This is kind of top heavy.
Most
Dangerous.
injuries and most fatalities in an earthquake are just due to things falling on top of you.
Yeah, and
It's really not because of structural damage to a house.
A shelf took a nosedive, but the house survived the equivalent of standing near the epicenter of one of America's worst earthquakes. The bearings and shock system performed proudly.
I'm really impressed. Those isolation systems, it's beautiful. I hope ours does that well.
Nick and Deanne's system will go through the same ordeal, but now with no rubber pad as added protection.
All right, so this is a real test.
This is it. Medium intensity, 4 inches this time.
Major earthquake.
Let me guess, you guys are feeling confident.
Very confident. Yeah. Deanne?
I'm confident.
All right, she's confident.
I'm
It'll be a
confident.
good time.
Ready?
Fired up.
Power on.
And speed.
Look at that!
That's so cool.
Oh my God!
Beautiful. It's totally still in there.
No problems. Even with no rubber pads, the system isolates the house from the tremors.
That is an isolation system,
That's
boys.
insane.
And time.
You can let it run all day, though.
Isolated inside.
It's amazing.
Let's go look at it.
And inside,
It's almost in perfect condition.
Yeah, what? Plant's still up. Alarm clock is fine.
Cardboard box down.
So the base is down, but I think that's actually when it started to slow,
Yeah.
and you know the ball bearings grabbed the pendulum.
Yeah.
So
Great.
Nice job, guys.
Come on.
done.
Admit
Well
you're
done.
impressed. Admit you're
I'm great.
impressed.
This is
How
great.
beautiful was that?
That was a pleasure to watch.
each system has excelled so far. Both successfully isolated a house from what approximated a 6.7 magnitude quake. But which works best? It's time to take them to the limit and beyond, into a realm no modern human has experienced. The team dials the shake table to its highest setting. The table will move 8 inches back and forth, twice as fast as it has in other tests. This will simulate a quake larger than anything on record, a maximum 10.0 on the Richter scale. It doesn't get any bigger than this. Chuck and Kevin's system has done well up to now, but the last test had it starting to buckle.
You guys ready to rock and roll?
Yeah! Okay, power up! The top's not even moving.
At the start, all's well.
Very nice. Oh my God!
You gotta be kidding me. Just let it crank. Just let it crank.
Oh, the stairs fell out.
Double time. All right, time. Time off.
That was 15 seconds. It went down in the 15th second. Okay, let me pull this panel off.
It's like a drywall disaster.
Yeah, I can make no sense of that.
There is our couch.
There's the couch.
The house collapsed, but it's not a total disaster.
The rug is up here. The table's still standing on 4 legs, though.
Right.
You know what? The top had 4 walls. The bottom only had 3.
It did.
So I think the structure was completely compromised with the 3 walls. And up top, it was kind of staying as a box. Just like a weight on top.
Hey, good job, guys, though. I mean, the isolation system worked until the very end. That was the 15th second. So you actually made it through the 15 seconds. But, I mean, it wouldn't have been a fit structure to live in.
I would not want to be in there.
That last one is off the charts.
Yeah, it doesn't happen.
And it stood up for a while. That isolation system was working.
Let's clean this mess up.
Clear it up.
And get the other one loaded up on here and see how well yours does. Good luck.
Yeah.
You guys set the bar high.
Next, Nick and Deanne's house.
I'm incredibly confident on this. I mean, seeing how well it responded to the last and middle test, which is basically our challenge.
But this one is a lot more.
I know, it's a lot of power.
Isn't it like a factor of 5 or something like that? Like ridiculous?
Well, there's only one way to find out what happens here. But now, you're absolutely confident, and you are?
I'm a lot more confident than I was before.
I don't blame you.
I'm pretty confident too, but I still think it's coming down.
Confidence is high, but will their system perform?
Power up.
It's perfect!
The quake shakes off the scale, but the house barely moves.
Watch it slow down now.
Yeah, I know. This is where it gets a little ugly.
Then it starts going back.
Not too bad. Good job, guys. Gorgeous.
After 15 violent seconds, the house remains intact. And the contents?
Look at that. It's just a vase.
Just about perfect. Even the alarm clock's still up.
That's amazing.
That is great. That is totally amazing. And look at how easy it is to push this vase off. It's just, you know?
It's like nothing.
Yeah, it's like nothing. The most damage we saw was actually from the first test, which seems ironic, but...
I know, the smallest one. But as soon as we got more acceleration, it completely isolated.
In major earthquake simulations, both ball-bearing base isolation systems succeeded. They could offer a simple, cost-effective way to counter a constant threat to life and property. With fine-tuning, these systems could revolutionize domestic quake zone construction. Analyzing footage in the lab, the team compares notes.
Ours did pretty well, but yours, unbelievable. I gotta hand it to you guys. That system, it was like your house wasn't even moving at all. I mean, barely moved.
Yeah, I mean, it was really pretty amazing. All the furniture inside stayed relatively intact.
Yeah.
I think it proves that a base isolation system can be applied to a house. I mean, the whole premise, right? The ground is shaking violently, and the house is isolated, not moving at all.
Yeah.
And the coolest thing is that this technology can actually be implemented into new home construction feasibly. Yeah, it can actually be used now, today.
I think so.
I live in New York City. We don't have many earthquakes, but I still want one of these systems under my pad.
The coolest thing for me is that the science was just unbelievable. Like, I'm still in shock of how well it went.